So hi everyone. As I said last time, free probability can be approached from different directions. That's kind of what's beautiful about it. It involves combinatorics, but also aspects of functional analysis and sister algebras and measure theory and complex analysis and so forth. And this course is intended to be a course for theoretical computer scientists, which essentially means that I'm not going to assume you know or remember much from measure theory or complex analysis. However, we will need some of the basics, definitions and results from these fields. And if you start at the wrong place, you'll need some time to actually fill in all the details by yourselves. So what I'm going to do in this lecture, which should take the whole lecture today, like 3 hours, is to give you like a brief introduction to measure theory, assuming you know nothing about measure theory. Okay, so the contact point for us, at least at this point, with measure theory is the fact that the Dirac measure, something that we talked about last time, I mentioned that again. Maybe I didn't use so many words, but the Dirac measure or Dirac function and so forth, just to give it formal grounds, you need to work with measures like sigma algebras and like abstract measures and so forth. So that will be the way I want to kind of motivate the reason you will need to understand measure theory. But actually the thing is that as you'll see next time, or maybe in the next lecture afterwards, we will need a lot of the results from measure theory that are related to Lebesgue integrals, which will allow us essentially to switch limits and integrals. These are things you cannot do at that generality that you will need with Riemann integrals, and you need a kind of more correct definition of Lebesgue integrals in order to do so. So measure theory for us will be both for the less important point of abstracting, giving formal grounds for what is the Dirac measure, but also to work with integrals as we would like to. But again, having said that, most of the course won't be too much about the like nitpicking aspects of measure theory. Nonetheless, I do think you should feel comfortable with everything that we are going to do there. It shouldn't be like the weird part of the course that you don't understand. It's something not simple, but something that with like 3 hours of effort we can make smooth. Okay, so let's get started. Okay, so let's start with measure theory 101. And as I said, I'm going to motivate it with the Dirac measure example that we have. So if you recall from last time, we had we wanted to have a distribution mu such that this holds, this equality holds. Namely, we started with the moments of a distribution. This was the distribution that corresponds to a matrix. These are all the eigenvalues of that matrix, namely the lambda I. And this is the corresponding moment where you take a to the k, a conjugate to the L. And we ask, what is the analytic distribution or star distribution in the analytic sense, corresponding, if exists, to these moments. So that's mu. And if we want to prove or to find such mu, then we need this equality to hold for any k and L integers larger or equal than 0, right? And the question, can we find this distribution? And if you think about it, it's enough to find the distribution mu for which this holds. So given a point, a number p, a real number p, you want to find a distribution that depends on that p. I called it here mu, but maybe you want to call it mu sub p or something, but let's call it mu, such that this equality holds, right? Because once this happens, you can take like the you can take the mu corresponding to each of the lambda i's and take kind of the average, like the 1 over d. out of the integral. So it's enough to consider one point. And anyhow, you need to consider one point if you want to. That's an easier problem, but it's the same problem. So here is the point. Probably so far, and I was vague on purpose so far. When you look at this thing, unless you're a mathematician, you study like math as an undergrad or something, you kind of said, well, this guy is just being weird. He means mu z times d to the z. Just a weird symbol for kind of a shortened notation for mu of z dz, where dz is just the part of the integral symbol. This is the course you consider the variable z there. That just tells you what's the variable you integrate. And mu z is a function, right? Like usual, like that's the usual thing you do when you do things. When you write something like an expectation of whatever, z to the k, you sample z from u and look at z to the k. What you really mean usually before talking about Lebesgue integrals is this thing, right? So the expectation is kind of encoded using this, and that's the function you take the expectation of. So let's see. So assuming you have this interpretation in mind, and that's going to be the wrong interpretation, when we need to fix that, then let's find mu z, right? So and again, depending on p. So given p, what is the corresponding mu or mu sub p? Well, if you look at it for a second, what you're trying to do in this integral is to kind of focus only at p, right? You want that integral to essentially ignore all the numbers that you integrate over, but for p, and only evaluate at p. So a good starting point would be this function, or this function. So before going to mu z and actually showing you that mu z, it's not a proof, but mu z doesn't exist, let's consider a mu sub epsilon of z. So mu sub epsilon of z is a way of focusing at p. What do I mean? So consider this function mu that's drawn here. So around p, plus minus epsilon to both sides, your constant 1 over 2 epsilon. I want the constant to be 1 over 2 epsilon because I want a probability measure. I want the total area here to be 1, right? And outside you're 0. That's kind of a way of epsilon. That's one way of epsilon approximating like this, focusing on p in formal statement. Right, so if you take this function mu of z, or mu sub epsilon of z, and you consider this integral, well, then what do you get? So I'm just plugging mu epsilon of z, so I'm integrating between p minus epsilon and p plus epsilon, right? And I'm integrating just, it's a uniform distribution in this range, so it's just 1 over 2 epsilon dz. That's a very simple integral. The 1 over 2 epsilon goes outside, and then the function corresponding to d to the k is 1 over k plus 1 z to the k plus 1, right? K is non-negative, it's not minus 1. And you just need to evaluate that function in the endpoints, p plus epsilon, p minus epsilon, and subtract. And when you do that, you get this expression. Now, if you look at it for a second, the first, so if you open this up using the binomial identity or whatever, you get p to the k plus 1 from here, but also p to the k plus 1 from here, which cancels out. And then you have k plus 1, choose one, p to the k epsilon here. And here you have the same thing, but it doesn't cancel out, right? It's a plus, because you have a minus here and a minus outside, and a minus outside. And then all the remaining terms are of the order of epsilon squared or smaller, where again, in my mind, k is fixed, p is fixed, and epsilon will go to 0, okay? So if you look at this and you kind of, okay, this went with that, here you get 2k plus 1, p to the k epsilon, and then some lower order terms, which if you look at it again for a second and cancel the k plus 1, the k plus 1, and the 2 and the 2, and the epsilon, you get p to the k, which is what you wanted, plus order of epsilon. right? So what I'm saying is that using this measure mu sub epsilon, you can almost up to an order of epsilon, you can almost do what you want. You can get this integral to be close to p to the k, but not quite. And you know, the only way you would know the only way I mean, what you infer from that is what you really want is to have a function which at p it gets the value infinity, like 1/2 epsilon as epsilon goes to 0, and only there, because the interval p minus epsilon, p plus epsilon shrinks. And by the way, it's not a proof that such a function doesn't exist, but because we know there is only one measure in the analytic sense, then you can, with some juggling, infer probably that's the only measure if exists. Okay, so what I'm trying to say here is that the function that you were looking for, it's not really a function, right? So you want a function that at p is infinity and otherwise it's 0. It's not a function. It doesn't stop people from calling it the Dirac function. Physicists use it all the time. They know what they mean by that, but it's not a formal definition. And we can either go that way and kind of turn a blind eye from that and say, well, it's not a function, but it's essentially the function that satisfies this relation, even though it's not a function. You can't do with it anything like you can do with a function except for integrating against it. So we can either do that, kind of goes in the physicist way, or do it rigorously, which is what we are going to do, okay? Because we want to prove things. So the solution, the right solution, that's not the only thing it fixes. It fixes a lot. The idea is not to consider d mu or d mu of z as a shorthand for a function mu of z times dz, which is just the symbol of the part of the integral symbol. Instead, what's going to happen is that we are going to define mu to be something which is not a function. It's going to be a measure. It's something else. It's not a function over the reals. We will see exactly what it is. It is a function, but not a function over the reals. It's going to be a kind of a more structured mathematical object. And what we will do is, after we're going to define what some measure is and so forth, we will be in a position to talk about what does it mean to integrate against a measure. So you see in the green here, which let me make red, this is going to be a notation, like an integral and a d. It gets two things as input, a measure and a function. You want to integrate against the measure. The function is going to sit here. That's the measure. And we are going to rigorously define this in such a way that, first of all, we can actually formalize what does it mean to be, what does Dirac measure actually means. That will allow us to find the analytic or the distribution in the analytic sense for the eigenvalues of matrices, or generally speaking, for measures where they have atoms, namely measures that have non-zero probability mass on points, right? Which is what we do all the time in discrete probability. And okay, we're going to do that. So we'll see, but that will take some time. So first of all, we have to talk about what a measure is before talking about integrating against a measure. Okay.